My name is Yichun Zhang. My web name is NGINX, and I'm the creator of OpenResty. And some of you have already been talking about OpenResty today. So we're so glad to talk in the Lua event today. It's my first time to talk in a Lua event. I used to talk to in Pro events, OpenResty events, and NGINX events, and Lua. Okay, so I modified my talk's title a little bit. It's not optimizing Lua code, but optimizing Lua applications. So the perspective is a little bit different, but I believe it's more interesting. And the target will be LuaJIT and OpenResty, of course. So what is OpenResty? Our highest level is NGINX plus LuaJIT, but we can plus much more in the end. And the process model is like this. We have an NGINX master process, and which forks multiple NGINX worker processes, and each of which has a shared LuaJIT virtual machine instance, so that all the concurrent requests served by each worker process are handled by a single VM. This way, we can avoid wasting too many LuaJIT VM instances. And it's also possible to share state very cheaply across all the concurrent requests in a single worker process. Yeah, we have a lot of hooks that you can hook your Lua code into different request processing phases of NGINX, so that you eventually can script the NGINX core very easily and on a very low level. And over the years, we also have accumulated many Lua libraries specific code designed for the OpenResty environment. Because we extend the Lua language, not the language, I mean extend the ecosystem with our own APIs. We will visit them later. And so these libraries will only work in the OpenResty environment. So talking about performance, we must talk about flame graphs. It's a very, very effective visualization method to find out bottlenecks in any running processes or even a whole production system. It's amazing. It makes me so excited over these years. It was invented by a systems engineer who used to work on the Solaris operating system. So he was some microsystems engineer, and he was so excellent. So what is a flame graph? I mock up a flame graph for my day. So basically, this is my day, 100%, right? So it's width. The width of the boxes matter, but the colors don't. So colors are just chosen by random. And during my day, I can spend, for example, this with like 30% of my time on processing emails from community. And during this part, which I can further divide this time into bug fixes and also verify user issues. So as we can see, the bug fix should take about 10% of the whole day, right? And verify issues is similar, right? And also hacking takes some time. So essentially, it's like a backtrace, right? This is like a main function, and this is process emails function, and the bug fix function is the calling relationship. So the backtrace grows this way from bottom to top. And the width of each function frame indicate the relative, ratio in the whole or some part of the parent or the ancestor. So it's very intuitive to evaluate how system resources are distributed across all the code paths. For example, CPU time is a system resource, right? And also memory usage, and also I/O. I/O can be measured in latency or data throughput, right? And also we can measure off CPU time. We will examine all these different possibilities later. So make sure you can interpret flame graphs easily. And regarding optimizations, we are more interested about the whole system because we don't want to optimize something that only takes about 5% of the whole, performance rate. We want to always optimize the bottlenecks. So a typical software stack consists of multiple layers or even more. So on the highest level, operating system kernel sits on the bottom. And in the middle is the system software like databases and HTTP servers or higher language virtual machine implementations like JVM or something. On the highest level is scripting languages like Lua or Perl or PHP, you name it, right? So most of us should be familiar with this layer, but few people know about the lower layers. But these bottom layers are so important that can, give us insights about why something weird is happening. So the layers are complicated, right? We have so many different things in the world. To make sense of these layers, especially in production environment, it's very important to have some advanced tool that can give us insight about how everything works right here, right now. So dynamic tracing technologies come to rescue. So basically, I personally use SystemTab to dynamically trace production online systems. So SystemTab is a baby from some Red Hat engineers, and it is it's not really core, but I believe it gets inspiration from dtrace, Solaris operating systems. And basically, how SystemTab works, it accepts a script file. Yeah, it has a DSL, and then we write a script file and feed it to SystemTab's stab tool, and stab tool compiles to a kernel module and inserts into the Linux kernel on the fly. And the kernel module makes use of the modern Linux debugging features, such as uprobes to probe the user space programs, and also use kprobes to trace the kernel itself. By means of uprobes and kprobes, we can safely inspect running Linux systems from user space to kernel space at the same time. That's an incredible capability. That's also how I spent my last few years, tracing the whole CloudFlare networks around the world to find out why some very weird issues are going. Yeah. Okay, I'll talk about very different performance metrics in the real world, from the most important to the least important. And the most dramatic thing that should deserve our special attention is I/O, right? Because modern I/O systems are still a bottleneck as compared to CPU. For I/O operations, especially in the NGINX world, we mostly concerned about network I/O. We want network I/O to be non-blocking so that network I/O operations will never block any operating system threads. That's the key to C10K, that is handling 10,000 connections at the same time. Actually, OpenResty can handle like 2 million concurrent connections in a single box without problem in production. We have such production users. They use OpenResty to build push systems to handle push requests from the mobile applications. And OpenResty has done a lot to ensure that I/O operations never block. But the user is free to use any Lua libraries out there, right? Even those born before OpenResty was born. So for those libraries, network I/O can be blocking horribly. To find such things, we have excellent tools. That is the off-CPU time flame graphs. I'll talk about off-CPU first, because the first flame graph in the world is all about on-CPU time. So what is off-CPU time? Off-CPU time is when a process, this guy is a process, it does nothing, right? It's not running code. It's not runs on any CPU cores. So this time, is off CPU time. When does this happen? When a network I/O operations, a certain force is dropping, then it puts the current operating system thread or the whole process into sleep. So this time we want to measure quantitatively, right? So we created an open source tool. You can find it on GitHub. So it's called sample BT. BT means backtrace, sample backtrace, or op CPU. And you just specify a process ID. It just requires 0 modification or collaborations from the target system you are probing. It's very important. It needs no collaboration at all. So you just specify PID just like you are using a GDB to analyze a process, right? And you can specify sampling time, for example, here for 5 seconds. And then it samples the process, generate a a.bt file. And then we use the standard flame graph tools written in Perl. It's from Brandon Gregg, the guy who invented flame graphs, and use these tools to generate a SVG file, which you can ship. You can display it in any web browser. For example, here's a real-world off-CPU flame graph obtained from one of our production servers several years ago. And so this is for NGINX, busy NGINX workers using little CPU time that is slow to process new requests. And we plotted an off-CPU time flame graph to figure out why it is slow and what is doing. So, like in the my day flame graph, the root is, for example, G2C, and the main function is here, right? So C programs should be familiar with the entry point. It's the entry point of any C programs. And then the flame graph, the backtrace grow this way, right? And on the tip, the most interesting parts are the tips of each flames or each towers. And we can see that it's open system call. And this is a semaphore wait. This is a lock, right? And this is a p-read. It's for reading files, and this is for open files. And this is sema-wait again, right? Semaphore is POSIX semaphore wait, and this p-read and open and semaphore wait to rename file. So apparently there are 2 things in this flame graph. One is a file opening and closing, and also reading a little bit. And another part is the wait, but wait is not significant, right? Sema-wait is not significant. Because in NGINX, most of the file I/Os, are not non-blocking. We don't have non-blocking file I/O, right? In this process, we're also not using operating system threads to, work around the blocking controls of the file I/O. So it's very apparent that we should optimize away the open parts, right? Fortunately, NGINX provides a file open cache to cache the file descriptors for us. So we just enable that, and these certain calls are gone. To verify that, we just have to, plot sample another flame graph to verify that they are indeed gone. So very easy, right? You can quantitatively measure how these blocking system calls affect your off-CPU time. I mean, the 100% of CPU time. Okay. Have to go quick. For network I/O, we are more fortunate because it supports non-blocking I/O mode. And what's interesting here is a synchronously non-blocking I/O. You can imagine how much I hate Node.js callback hell, right? So in Lua, fortunately, we have coroutines that we can take advantage of. But coroutines are still very basic abstractions, and I implemented live threads, emulating a POSIX thread API, but it has nothing to do with operating system threads. It's all user space. It's based on coroutines. But I implemented a user-land thread scheduler, and the threads can be scheduled automatically. You don't have to resume or yield. Everything is taken care of automatically. And also we have user-land semaphores so that you can safely synchronize many concurrent live threads very easily and safely. And don't worry about deadlocks because semaphores always have a timeout. here's a quick example. We can spawn a new thread, and after this line, it returns immediately. So back to the parent thread, right? And the child thread just created, keeps running asynchronously in the background, scheduled by the OpenResty thread scheduler. Very efficient. And also we can wait. For example, the parent can wait on its children. So it's a sorry about that. Okay. So it's essentially like a join, thread join. So we don't have many different operating threads here. We only have a one system thread per worker process. And this operating system thread is like a boy pushes the cards forward in turn when a particular card can be moved, right? That is when a new I/O event occurs. So that is how it works. It can handle like tens of thousands, hundreds of thousands of concurrent threads very efficiently. And we can also queue. I also implemented an abstraction of coroutine-based sockets, and it's 4 duplex, which means that we have 2 light threads automatically, concurrently operating on the same code socket without conflicts and without locking. Because as long as one thread is reading from the code socket and the other thread is writing to the same code socket object. So it's 4 duplex. Also, we can, for example, every connection is, every operations are similar to the Lua socket library, and each, for example, connect returns until the operation completes. So you don't need callbacks or anything. And also SSL handshake. We also have timers and sleeves. For example, you can check out the OpenResty manual very quickly. And so for timers, synchronous, similar to LightThread, but it's detached from the current session completely. And also we have synchronous sleep, which is also non-blocking, never blocks any operating system threads. Okay, so next thing is CPU, finally. CPU is also very important when we make most of the I/O operations non-blocking. So CPU can be the next bottleneck. We have on-CPU flame graphs. So on-CPU is when the process is actually running on a CPU core, not a particular core, but on any of the CPU cores. And we can sample. So sampling is very important. We don't want to instrument every function core or anything like that. It's too expensive for production. Sampling can give us very good statistical results with very little overhead. This is also a flame graph sampled on one of our production servers. And we can see that most of the CPU time is spent on, for example, dplate slow. This is from zlib for compressing the web pages before sending it out. Okay, and also some part of the flames don't have a backtrace, right? This is because of the just-in-time compiled Lua code. Because for JIT compiled Lua code, they don't have debug symbols, so we don't have backtraces. And also it includes PCRE compiled code, because PCRE also supports just-in-time compilation, right? And sometimes we can even find bottlenecks in LuaJIT itself. For example, this is a real bottleneck spotted in production, which reviews that LuaJIT, this function, is a standard C API, right? But LuaJIT's implementation of LuaJIT has some little bit higher overhead because it's on Winder, stack on Winder. And I reported this to Michael, and Michael took a quick glance on this, and he quickly implemented a fix and make it go away from my flame graph. Oh yeah. so as you can see that everything in the user land can be saved from a single graph, no matter what. So you can focus on 2 bottlenecks without assuming too much about potential culprits. And if we wish, we can include kernel space backtraces in the same graph as well, if we wish, right? So we can't lose any culprits. in a frame graph. So it's very important. You have to look at the big picture. For optimizations, it's easy to go wander into small trails and other things, right? And we can also have Lua frame graphs one level up. So the frame graphs we've seen so far is CLand or assembly code land frame graphs, but we can make the function frames in the frame graphs to be Lua functions. The business level frame graphs can be more useful sometimes. For example, this is a frame graph for CloudFlare's WAF. So Robert talked about WAF in the previous presentation, and CloudFlare also has a WAF. It's proprietary, it's not open source. And we can have the frame graphs, function frames to be functions, Lua functions. And the first part, it's not very clear, right? Let me click on the real frame graph here, and you can see that, for example, this one, WAF for the Lua is a file name, and underscore test underscore bars is a function name. So you can have both the Lua file name and the function name, which should be good enough. If you want, you can have the granularity of single lines of Lua code, if you wish. But the graph maybe may look a lot messier. Okay, let's go back. Separating the Lua frame graphs is similar, just with another tool. LJ Lua Stacks is also a system tab tool. You specify how long you want to sample. So it's important. Just during these 5 seconds, we have a small overhead. It's like 20% or much lower, like 10% overhead to the target process, because we have multiple processes, right? So only one of them incur this overhead. And after the sampling is finished, the target process here will resume its original full speed without any penalty. So no restart, no reload, no changes in code, no IP tables, nothing, right? Okay, so it's basically a PID, and then you're done. You generate a vector, they can generate a frame graph. And LuaJIT has also a built-in profiler. It's new, it's in 2.1, right? But it's not so useful. It's useful, but it's not so useful as compared to the system tab-based sampling I just demonstrated. Why? Because the LuaJIT built-in profiler has to work in the application itself, so its capability is quite limited and has to make a lot of trade-offs, like flushing out all the compiled traces, and from here generate special profiling-aware traces. And after the sampling, the profiling is over, it flushes out all the profiling-aware traces again, and then from then on, generate ordinary traces. So trace is a compiled unit of compiled Lua code. So it incurs a much higher overhead and much more fluctuations in the Lua code performance, right? But for system tab sampling, LuaJIT has no knowledge about what's going on, right? And it's also very clean. It does not change any state in the target process. Okay, I have to hurry. And for dynamic applications, garbage collection can also be a bottleneck, especially on the Lua land. So for Lua tables, these LuaJIT primitives can often show up in your frame graphs, especially on CPU frame graphs. So LJ tab new is for creating a new table. Resize is when LuaJIT has to resize the table. And tab len is for calculating the length of an array-like table. So LuaJIT implements a table new API. It's a Lua API, new API, not in the standard Lua language, but it's LuaJIT's own baby. And I proposed this change to my fork, and we happily implemented that. So with table new, you can avoid the initial resizing of Lua table by specifying the initial sizes for the array part and the hash part of the table. Also, there's a table clear API that you can clear a table without freeing the table. It's very important because the annotations are expensive. You want to recycle the Lua tables as much as you can. So before reviewing a table, the simplest way is to clear up the table, zero out, right? Another feature is that Lua tables has a quirk that if you frequently remove keys and adding new keys, it will trigger table resize. That's not, even if the total number of the keys are fixed. So this is very annoying. That's why we implement a pure FFI C data structure implementation of hash table in our LRU cache library. Okay, Lua strings. So we should never use this, right? Because Lua strings are interned. We should use table concat. Okay, that's quick. And we shouldn't use string.sub to create too many substrings because Lua strings are garbage collectible objects, right? We should use string.byte to inspect a single character so that this function returns a number, not a GC functions to be collected. And Lua functions can also be, expensive when you're creating a lot of Lua closures on hot Lua code paths. It can be, very fuzzy because every Lua function declaration is essentially an assignment and a dynamic closure creation. So this thing can easily show up in a plain graph like this, BC FNU. So this is a bytecode, right? The LuaJIT bytecode for creating a new function. So when you see this, you know what's happening, right? You should put the function on the top level and avoid it on the hot paths. JITting versus interpreting, Robert mentioned LuaResty core. That's a different implementation of the Lua API in OpenResty. Originally, we used Lua C function, the standard Lua API, to define C functions in Lua, but it cannot be just-in-time compiled. We need to use the FFI to core into NES Lua directly. And LuaJIT works like this way. It has a fast interpreter, much faster than standard Lua 5.1 interpreter usually. And it also has a compiler that generates native code when the interpreted code gets hot. The input is a bytecode. So this is how LuaJIT works, essentially. And we really want to just-in-time compile as much as Lua code as possible, right? So LuaJIT provides some standard libraries, JIT.v and JIT.dump, to help you analyze which part of your Lua code cannot be JIT compiled or why. And we also provide the Lua flame graph tools to get interpreting only flame graphs and the JIT only flame graphs so that you can see how your CPU time is spent on JIT and non-JIT code. Also, this culture in the tracing compilation, basically for code branches like biased and unbiased, LuaJIT is particularly good at biased branching. For unbiased, like two branches, each take 50% of the time taken, that is bad. That's very bad. And so we propose the Lua code generation on top LuaJIT to fix this problem. So instead of writing evaluator like Lua code to interpreting some data structures, you really generate a single linear Lua code without too many branches. Or you have branches, but those branches are for error handling. That's fine because that's biased, right? It's like a JIT over JIT. I found Mike Porter himself use this trick a lot in his computer game shootout benchmark programs, and that's very interesting. So this way we can beat many Java programs very easily. Seriously, and even C. And using just a fraction of the total memory footprint of Java. Regular expressions. So some guy says that
you need a frame graph of your presentation.
I'm sorry, I walk through. Okay, I'll give no explanation. So regexes can be readable because we can use space, ignore space mode. So it's not really messy. And most of the regex engines use backtracking algorithms, but we don't have to, right? And so I wrote a regex engine in C in the past 3 years. So sregexes is crazy, and you can do data streaming, infinite data streams, matching with fixed memory footprint, like 4K buffer, right? And the benchmark is very promising for those read to it sucks. So higher is better. Speed. This is speed. It's megabytes per second. And PCRE JIT, PCRE 2 JIT does a good job, and we are very close, right? It's sregexes DFA, so this one. And read to is here. And another sample, so we wins. A little bit, right? Because for good cases, PCRE does such a good job that when it sucks, it really sucks. We are consistently better, right? It's like what, 21 gigabytes per second, right? So, and all others suck, right? And another example here, yeah. So read2 sucks, and PCRE JIT a little bit. And for this one, yeah, this regex is from law security, yeah, from law security rule set, and it's real regex that makes our production machine burns, right? So with DFA algorithm, it's a non-backtracking algorithm, we can do so much better. And for time complexity, a DFL implementation can guarantee ON complexity, so linear complexity guarantees. And also for space complexity, when the regex is fixed, we can guarantee O1, right? And other things can be exponentially expensive in corner cases or on malicious input. Okay, memory. We have memory leak flame graph, and we use this flame graph to locate a real memory leak in the NGINX port, the stock NGINX port. And also we have wonderful garbage collecting object analysis for LuaJIT. So you can use the system tab tool to find out how many and how the size is distributed in each Lua tables, Lua strings, Lua user data, everything, right? And also the compiled Lua code objects, trace objects. Yeah, and we also have GDB equivalent, which can be used for offline analysis when you have a cooldown. Right? You can actively generate a cooldown even when the process does not crash, right? And also streaming processing again. So this way you can use constant small memory footprint to handle theoretically infinite lengths of data stream. It's so powerful, but the techniques and algorithms involved here is quite complex. That's why we created sregexes for this. It's still under development. You can watch us on GitHub. So abstractions has a cost, as we can see, like functions, like tables, like strings, but we also have huge opportunities of new abstractions on a higher level. So I propose a business level demands specific language. So it's a new era for OpenResty, apparently. So I don't have the time to dive into that because it will take another hour or two. So most creative syntax sucks. I have to say that, even though it's a DSL, so abstraction matters. Okay, any questions? Fortunately, we have a coffee break, right? Okay, questions?
So the JIT over NGINX stuff, you mentioned something really cool. Do you have any specific suggestions on how to test?
I cannot hear you.
Oh, about your Lua code generation stuff.
Code
JIT over
generation.
JIT, do you have any specific suggestions on how to achieve that?
I think the key to optimization is to specialize, right? Specialize your code for a particular setup. Taking the CDN server as an example. So we have millions of users, right? Millions of different customers running their origin sites behind us, right? And each site has different configurations, right? We can specifically generate a Lua CDN for each customer according to their current particular setup and makes the logic very linear, right? So that For example, if we have 100 features and the user only use 2, right? So we can only generate code specifically for these 2 features, so without worrying about the rest 98, right? So this way, so this is an example that can give you some good idea of how specialization and code generation works.
Great, thanks.
Sure.
The frameworks are really interesting. Can you go into how you were able to pull the Lua stack straight into plain graph?
Oh, it's very easy. We need zero collaboration from LuaJIT. I'm very proud of that. At the cost of a little bit, inaccuracy that is bearable. And basically, what we do is to kind of duplicate LuaJIT's existing backtrace dumping function in the system tab script. We duplicate that, but our duplicated version has the advantage of that it's always safe, even when it tries to read some unreadable memory regions. It's safe because the kernel, the Youku protects that, the system tab protects that. Okay, so this is also how we implement flame graphs for other languages. For example, Perl. I also wrote a flame graph tool for Perl, and in Perl I just port the Perl backtrace dumping functions in the Perl VM over to the system tab environment. Yeah. So most of the time the code already exists, right? You just need to find it out. For example, the GC object dumping tools. How does that work? It's very simple actually. It just repeat the mark and sweep process inside the LuaJIT VM. So for the mark process, we just gather all the GC functions, even though they are dead, right? But they are not connected. So this way we can collect all the LuaGC functions and output their aggregations very easily. So this is just a mark. And we also have a tool to duplicate the sweep phase to find out real live GC objects. Yeah, you can find it out on GitHub. Yeah.
So you mentioned more about avoiding blocking calls. So right now the only thing that you provide for non-blocking stuff is co-sockets. When will we see things like opening files and processes and things like that?
Oh yeah. So we have plans to expose the AIO API in the NGINX 4, so which can utilize native API on capable operating systems like FreeBSD. On Linux it sucks, but it's still works, right? To some extent. And also, NGINX provides a threads AIO mode that it has an internal operating system thread pool that can be used to work around the blocking file IO.
So you're saying that we would launch a blocking thread and you're blocking things inside?
It's still blocking,
yeah.
But we just use threads, dedicated threads, to offload that. In some cases it's better, but in some cases it can be worse. So depending on your use cases and how fast your disks are, right? Yeah. So we are working on the AIO API. Yeah. Any other questions? Okay, cool. Thank you very much.